Okay. Today we'll talk about poisoning. We'll continue talking about poisoning. Last time we said poisoning is an attack in which a fraction of training data is controlled by the attacker and manipulated to subvert the learning process. Well, how does poisoning work? First, I'll give you a very intuitive description of how poisoning works. So imagine you have a set of training data. In this scenario, you can think of it as a sample, but there are a lot of examples in the sample. So in the training data, let's say you have a base image. Of course, I'm showing one example here, but I could potentially poison a fraction of training examples. So you have a base image, and now what do? You perturb the base image. You somehow craft some perturbation, which is almost invisible, or depending on your threat model. So usually people think that these perturbations are really small and sometimes not noticeable. Then you get a poison. So after you add these perturbation to your base image, you get a poison, and you go you put the poison back to your training example. Now your machine learning algorithm, maybe your neural network, maybe your SVM machine, or whatever machine learning algorithm you're using, your machine learning algorithm is going to train as normal, but it's trained on this poisoned training data, right? The fraction of the training examples will be poisoned. So normally, if you don't have the poison, if you have such an image here, as I'm showing here, usually would classify it as a plain, right? However, if you add these kind of poisoning to your training image, then in your test time, when you have such an image, you would unfortunately classify it as a frog. Okay, so, but this is an example of how poisoning works. But first, before we understand, how to design such a poisoning mechanism, why is poisoning bad, right? So, you have the base classifier, you have the perturbation, you get the poison. The reason why poisoning is bad is usually attacks are hard to detect. And even with human eyes, is probably a little bit hard to detect. So also usually they have clean. You could imagine there are other kind of poisoning, which is, shifting the label or something. But usually, if you have a clean label, so, which basically means that poison are labeled correctly, then it is really hard to detect. Also, the performance only changes on selected targets. Usually, that's how some of the poisoning techniques work. If it is a targeted poisoning, so only changes on selected target. So if you have, if you kind of examine the performance of the classifier, and you somehow you have a lot of classes, you just miss this class, it's likely that you won't notice the strange behavior of your classifier. Also, attackers can be executed by outsiders, right? So, so because of the cloud sourcing, so machine learning algorithms nowadays require a lot of data to be trained, right? Especially these large neural networks require a lot of data. So where do you get those data, right? You can use mechanical Turks, right? Or sometimes you can even use experts, but you cannot guarantee that the data that you're collected from are usually you can trust them. You cannot guarantee that, right? The poison can just be placed on the website, or can be sent to the data collector, right? So basically, that's why poisoning is a very important issue, security issue we have to consider for machine learning algorithms. The effect of poisoning is also really bad, because if you have your classifiers poisoned, right? So then what happens is that, you because in industry, once you train a neural network, you're going to use that neural network for all subsequent tasks, right? For all the predictions from every customer you have. So it is it's very dangerous, right? You could have catastrophic failures on these future prediction tasks. Poisoning is especially bad in two contexts, right? First is the transfer learning context. What do I mean? If you have a pre-trained network used in your machine learning, then poisoning is particularly bad because the pre-trained network could be poisoned one, right? You don't know whether you should trust this pre-trained network or not, right? And in a lot of scenarios, the transfer learning scenarios is that usually the feature extraction layers are frozen. I'll talk about that later, what we mean here. And they would only retrain the classification layers. It's very common in industry because these networks are just very difficult to train. And sometimes you don't have enough data to train them. So that's a lot of, it is very common in a transfer learning scenario that you've frozen the feature extraction layers. I'll explain what that is soon, and then just retrain the classification layer. Even in the end-to-end retraining framework, in the context of end-to-end retraining, sometimes, the pre-trained network is used. This is also the problem, especially why poisoning is especially bad, because if you use a pre-trained network, this pre-trained network could be poisoned. Even if you train all layers, retrain all layers, you started with something that's really bad and potentially could still be stuck in that kind of bad region. So we see some poisoning in classical tasks, right? So people have started a lot of poisoning attacks against popular learning algorithms like support vector machines, lasso, logistic regression, regional regression, and so on. And they've been successfully applied to spam detection and malware detection. So you can just have poison data injected into the training set, and the spam detection would just fail, or malware detection would just fail. Okay, so we've talked about this poisoning in classical tasks, but of course, apparently we're focusing on poisoning in neural networks, and today we will first give you a more like empirical understanding of how to design a poisoning through a kind of simple mechanism. And then later on, we're going to talk about from an optimization point of view, how poisoning problem is a bi-level optimization problem and how we can solve it, right? How usually people solve it, or what are the drawbacks of the traditional methods to solving this, and how these methods could be difficult to be applied to deep neural networks. So, apparently, I don't know if we can finish talking about the defense of poisoning today, but hopefully we'll cover the attacks of the poisoning. Okay, so before I start, I just wanted to motivate why I talk about poisoning attacks, right? So poisoning attacks is very important because if you don't understand the power of poisoning attacks, of course, under some constraints usually, then it's hard for you to defend against them, right? So, you have to know your enemy to defeat them, basically, that's what they say. So let's see how we can design a poisoning attack. So this paper is from Tom Goldstein's group. Tom is our faculty here. So you can also find the archive link of this paper. This is a so-called collision attack. So, let fx to be the function that propagates an input x through the network to the panel, so the layer before softmax, right? So let's see. So this is what we call the feature extraction, or the feature extraction layers. So, we call the activations of the layer the feature space representation of the input because it encodes high-level semantic features. So the thing is, because it is the function f, which could be a neural network, it doesn't have to be, due to the high complexity of nonlinearity of the f, it is possible that you can find such an x. Oh, what happened? You can find such an x here. Oh. Let me see. Yeah, you can find such an x. Let me use my cursor here. That collides with the target in the feature space. So what is the feature space? F of x is in the feature space. F of t is also in the feature space. X is an example and t is your target. You can think about a target as a plane, and x is some example that you optimize over, okay? So you can make sure that this x kind of collide with the target in the feature space, and simultaneously it's also close to the base B. So B is the frog, let's say, in the input image space. So it's x minus B. Okay, so it is just x itself and B itself in the input space. So, this is due to the non-convexity of F and the complexity of F. You can make sure this happens, right? So basically you can just compute, you can just solve this optimization problem here. So it's gonna be your P. X is gonna be your P. Make sense? Right? So the rightmost term is, causing the Poisson instance P to appear like a base class instance to a human labeler, right? Because the P is going to be very close to B. So it looks like a frog as a human labeler. It would very likely label it as a frog. And this beta parameter here is, the degree to which this is very close to a frog, basically, right? And the first term here is just causing the Poisson instance to move toward the target instance in feature space, right? And then it will get embedded in the target class distribution. So on a clean model, this Poisson instance would be misclassified as a target if the model is retrained on the clean data plus the Poisson instance. However, the linear decision boundary in feature space is expected to rotate to the label of the Poisson instance as if it is in the base class, right? Since the target instance is nearby, then the decision boundary rotation may include the target instance in the base classifier along with the poisoning instance. Right, so this allows the unperturbed target instance, which is just misclassified into the base classifier during test time. So, people sometimes say this is now a backdoor into the base class. Does this make sense? So this is why in the transfer learning scenario, we're saying, when we're saying why poisoning was bad, is that one context is transfer learning scenario that, the feature space sometimes is all frozen when you're doing retraining. So, if you have something, your X, your F of P is close to F of T, then it is very likely that the space classifier will be very close to the target in the feature space. That's why it is a poison. Okay, so these are some slides. These are some examples of how the poisoning works. So this poisoning instance are made for fish class from dog-based instances on the top. So you can see, with all these kind of you know, base, this is a base, clean base, and then you have all these perturbations, you know, from a human point of view, at least I cannot see any difference between these figures, right? But somehow by injecting these figures, you will be classified, you know, you will basically classify all those fishes as a dog. Okay, and similarly, you could also use fish as a base as a clean base, and then you can design all these poisoning made for dog class from fish base. So then all these dog images will be classified now as a fish. Okay, so these are some examples we can see. So basically, this seems to be a very simple idea of crafting poisoning examples using so-called collision attacks, right? So now, you know, so then the question is, why does this work? Basically, the paper provides a explanation. It says that, you know, you have basically your feature extraction layers are frozen. So it is easy to move classification boundaries in final layer. And because the last layer has lots of weights, so you can easily just move classification boundary. Apparently, you know, this image shows that, you know, the attack works pretty well. You can see, you know, the misclassification confidence, the poison model do have a pretty good misspecification confidence. Okay, as you can see, some of them are even close to 1. Okay, so, you know, it seems to be very nice, but one thing this paper does acknowledge is that it actually fails on end-to-end networks. So if you don't freeze the feature extraction layers, but you're training from end to end to solve that optimization problem we saw in the previous slides, then it will actually fail. So basically, this means that it is to solve that optimization problem, it is not so easy. And it only, you know, in this scenario only works, in their experiment only works when the feature extraction layers are frozen, and then you just retrain the classification layer. Does the attacker need to know the architecture used by the system? So that's a very good question. So, you know, in this scenario, I would say, so let's go back to this optimization problem. So I think, you know, Aliot, sorry, I might have pronounced your name incorrectly. I think you're right that it is not necessary, and some papers are black box. But in this scenario, I think if you have to solve this argmin problem, then you have to know the F. So in some sense, you have to know what is the output after the after feature extraction layers. Okay, does that make sense? Yeah, okay, perfect. So these are, you know, so now I just wanted to say that, okay, go back. So it actually fails on end-to-end networks. And, you know, the takeaway message is that it's tough to fool the feature extractors. You know, so basically the feature extraction layers learn to ignore adversarial perturbations. So by the time features get to classification layer, they're just gone. Anyway, but this paper, I just wanted to show you how poisoning works and then how empirically you can understand it, and essentially the difficulty of designing poisoning attacks. Okay, so that's that. But now I'm going to talk about a more general optimization framework and a more formal formulation of poisoning attacks. So, you know, before that, let's first understand what's the major technical difficulty here. So the major technical difficulty of designing poisoning attacks is the computation of poison samples, or like, so-called, sometimes you call it adversarial training example. The major technical difficulty is that it requires solving a bi-level optimization problem. So what do I mean by that? I don't have the math equation here because I haven't introduced some notations, but I will first use English, sentences to describe what do I mean by a bi-level optimization problem. So the outer information, let's see, did I record my lecture? Is it recording?
It's recording.
Okay, thanks. Okay, so just want to make sure I don't want it to realize that I didn't record. So, for the bi-level optimization problem, the outer optimization is to maximize the classification error on an untamed validation set. Okay, and then there is some inner optimization correspondence to the training, the learning algorithm on the poison data. So what do I mean by that? First, let's look at the inner optimization. So the inner optimization is almost like it's my attacker, right? So as an attacker, I'm trying to find, I'm trying to find training examples so that the the learning algorithm. So how should I say? You're basically trying to use you want to find the poison data such that the training algorithm, you would want, okay, I see. So you want to find the poison data so that you would train a classifier. Does that make sense? So you would have like, imagine that you have some poison data, and based on the learning classifier, you would imitate what the learning classifier or the classifier is doing. So if the classifier use the poison data, is going to learn a parameter of the neural network omega, then that's going to be your result, because the neural network will have to minimize some kind of loss function, and they would come up with an omega, right? So that's the inner optimization problem. It's like an imitation of the learning algorithm. Then outside of this inner optimization, there is an outer optimization problem. What is this outer optimization problem? It's essentially maximize the classification error on the untamed validation set. So what does this mean? This means that I wanted to find such a poison, right? Is that true? Let me think. Yeah, let's see. So I think this is a little bit confusing here. Let's go to the next slide. Maybe it's more clear. So basically what I wanted to emphasize here is this bi-level optimization problem depends on, both the poisoning, how do I design the poisoning, but also depends on if I design the poisoning, the learning algorithm would have to learn a corresponding classifier. And I wanted to make sure that that classifier does very bad on my on the untamed like validation data sets. So maybe this is not very clear, but let me first finish like usually how people solve it, and we can see a more concrete optimization formulation here. So how do we solve it, right? How do we solve this bi-level optimization? A gradient-based implicit differentiation is often used. So basically what people do is to replace the inner optimization problem with its stationary conditions, or so-called KKD conditions, to derive an implicit equation for the gradient. So, but it is actually the drawback of it is apparently, it has a very complex procedure that you have to use to compute the required gradient. So definitely, due to computational complexity, only works for a limited class of learning algorithms. Usually it doesn't work for deep neural networks. So the contribution of this paper is to exploit back gradient optimization to implement a much more computationally efficient poisoning attack. And the idea is just to compute the gradient of interest through some backpropagation, and while reversing the underlying learning procedure to trace back the entire sequence of parameter updates performed during learning without storing it. Okay, so, but I wanted to introduce the ideas more concretely. So this paper focused on classification, and usually, right now most of the works in poisoning is focusing on classification. So the goal is to given an instance space X and the label space Y, the learner aims to estimate the underlying latent function, or in our learning theory, the terminology is called a target concept, right? So you wanted to learn a latent function f that maps x from y, from x to y. So given a training set, you have n such examples from the underlying probability distribution pxy, we can estimate f with a parametric or non-parametric model. You oftentimes, let's think about parametric, is simpler. You've parametric model M trained by minimizing the objective function. So here is your objective function, the curly L. So this curly L is the objective function for the learning algorithm. It is trying to kind of course, you wanted to minimize this objective function. Usually is just a tractable estimation of the generalization error, right? Now, so what is really important in a threat model for designing attack algorithms is to understand the attacker's knowledge. So this paper, I think, has a very good description of the attacker's knowledge. Basically set up a framework for us to understand the attack. So, you have the perfect knowledge attacks, which is not practical, but it assumes that, the attacker will know the training data, know the feature set, know the algorithm, and know the parameter of the learning algorithm. So, apparently it's not very practical. In practice, that's just usually not what attackers knows, but it still gives us a worst case evaluation of the security of the learning algorithm. So sometimes it's still useful for understanding in a worst scenario how secure your learning algorithm is. There is this limited knowledge attacks, and those are more practical. And there are two types of them. One is the surrogate data, and then the other is the surrogate learner. Apparently, based on the name, the surrogate data just means that you don't know the training data, but somehow you have a surrogate. So you have an estimation of the training data, or you can just devise your own training data set. You know the feature set, you know the input space, you know the learning algorithm, but you don't know the parameters. You can estimate the parameters though, right? So if you know the learning algorithm, you can just, imitate the learner to estimate your own parameter. Although this will be computationally expensive, but that's what you can do. And in a surrogate learner scenario, according to the name, is that you assume you know the training data, you know the feature set, but you don't know the learning algorithm. So you can, imitate the learning. You can take a guess of the learning algorithm. Sometimes they call it a surrogate algorithm. And of course, if you don't know the algorithm, you also don't know the parameters. You could estimate the parameters based on your surrogate algorithm. Okay. So these are the two very popular models that people use often. So now, once we know the attacker's knowledge, attacker's capability is also very important. It's based on the influence of the attacker has on the input data. Also, it's built on the presence of the data manipulation constraints. So those are the attacker's capabilities. So in terms of the attacker influence, it can be causative influence or it can be exploratory influence. What is a causative influence is just, it means just the attacker can influence both training and test. And this is why we call it poisoning. Usually, if we can influence the training, then it is often called poisoning. But exploratory influence usually is what people are more familiar with, the evasion attacks, right? So it's only manipulating the test data rather than the training data. Okay, so today we will be focusing on the poisoning. Now the other important aspect of attackers' capability of the data manipulation constraints. So of course, the presence of the constraint is on the manipulation of the input data, right? So in a evasion attack, people are familiar with this LP norm perturbations or like more advanced patch perturbation or, some kind of, human perception and so on, right? So those are so-called the presence of constraints on the manipulation of the input data. This basically kind of tell you the power of the attacker. In more commonly in the poisoning attacks, so you have like so-called the initial set of attack examples. So DC is the attack examples is given, and it is manipulated according to a space of possible modifications. So this is a very abstract way of describing it. They are just using phi of DC to denote, you have to satisfy some constraint for this set of attack examples. One thing I want to clarify is that in machine learning literature, a lot of people try to kind of, mix samples and examples. In this scenario, the paper is the samples, but I think it just means examples, right? Samples means just, one sample means a set of example. So, sometimes these papers interchangeably use samples and example, but I think it's easy to figure out what it means in the context. Also, this field DC here seems to be, sorry, this is theta, right? I think, yeah, okay. The theta of DC here seems to be very vague. Usually, if you think about a like LP norm perturbation, it just means that the perturbation cannot be LP norm. It has to be LP norm bounded within the clean example. The difference between the two, if you measure the difference between the two using an LP norm, then the LP norm cannot be larger than some threshold epsilon, right? So, but here this theta DC is just very, I would say, abstract, right? So it doesn't specify. In order to make this framework more general, the authors here don't specify specifically what is the constraint of the data manipulation. Okay, so now the attack strategy, right? So the attacker's goal is given the attacker's knowledge, right? So, it is either a perfect knowledge or surrogate data or surrogate learning algorithm, so on, right? So given the attacker's knowledge and a set of examples that it could manipulate, right? So these examples after manipulation, it has to be, within the theta of DC. So it has to satisfy the constraint, the data manipulation constraint, right? So the attacker's objective function will be denoted using A of DC prime theta. So A just means this is the objective function of the attacker, So, they were using A, just it's easier to understand. And DC prime, it just is the manipulated examples, right, after manipulation. And the theta is just the attacker's knowledge. Okay, so apparently the objective function will depend not only on the manipulated examples, but also on the attacker's knowledge. So this function will evaluate how effectively these attackers are able to manipulate the learning algorithm. And it's obvious that the optimal attacker strategy is to find the DC star, how you manipulate this example so that you can maximize A of DC prime theta. Okay. Okay, so someone's saying, Joy is saying, can you give us an example of evasion attack? Oh, yeah, sure. Evasion attack is very simple. So let's go back to, where did I? Okay, so here is the attack influence, right? As I said, the poisoning attack is where you can inject the perturbed image into your training example, and then your learning algorithm will have to learn from the input examples, right? But evasion attack is different. Evasion attack is only during test time you can manipulate the images. For example, if I've already learned my neural network, right? I don't know whether it's poison or not, but in terms of evasion attack, I don't care. I just have a base classifier like a neural network that's there. And evasion attack just means that during test time, when I have a image frog, right? So, the attacker is going to manipulate the frog, somehow add some noise. And now after manipulation, after the adversarial perturbation, this frog will be classified as a plane. Okay, so that's what we mean by evasion attack. So it's basically the attack influence, right? So this attacker, if the attacker can influence both training and test, then it's poisoning. But if it can only manipulate the test data, then it's evasion. No problem. Okay, so let's go back to this. So we had a little bit of confusion about understanding the bi-level optimization problem, but now, we will make it much more clear once we've introduced all the notations about, what is the objective of the attacker and the attacker's knowledge and data manipulation constraints. Now let's look at the poison attack scenarios. Okay, I don't know, is it too small to see? Or is it fine? So first of all, I wanted to say this error generic poisoning attack in contradiction to, in contrast to the error specific poisoning attack. So before, the example we saw was, we always poison a plane into a frog, right? So, after injecting that poison, then whenever I have a plane image, I would classify it as a frog. So that's called an error-specific poisoning attack, or sometimes people call it targeted attack, because I have a specific target. I will classify, planes as frog. That's my specific target, based on the attacker's will, of course. But there is another class of attack, which is the error generic poisoning attack. What does that mean? It means that I don't have a specific target in my mind, but I just wanted to cause generic misclassifications, right? I don't care whether you classify, the plane into a frog, or the plane into a, I don't know, cat, or I don't even care whether you don't misclassify planes, you just misclassify other things. As long as you have a low classification accuracy, as an attacker, I'm fine, right? So that's the goal of the attacker, not aiming to cause specific error, but just generic misclassifications. So, now let's clarify what I mean by a bi-level optimization. Here we have a specific optimization problem put in here. So this is a bi-level optimization. Why? So see, we have this outer optimization problem. What is it? It's to find the manipulation of the data. So DC star is just argmax of DC prime. DC prime, this theta of DC is just the data manipulation constraint, right? I cannot do arbitrary manipulation. I have to manipulate it in a way that is allowed, that won't be attacked or won't be detected very easily or something, right? But anyway, this is my threat model constraint, data manipulation constraint. So I have to do argmax of DC prime. As long as DC prime is within my data manipulation constraint, then I will maximize my attack objective. Okay, so I have an objective function wanting to maximize it, which also is just like you wanted to maximize the loss of the the loss on the evaluation data set and a corresponding omega hat that I think the learner would learn if I give them the DC prime. Does that make sense? So this is a little bit hard to understand. First of all, because this is error generic poisoning attack, so the objective of the attacker is just the loss function evaluated on the validation set, right? Okay, so the validation set is something that I can estimate because I don't know what will be evaluated, but I can estimate, right? I can have a surrogate validation set. So it's the val hat. But more importantly, how I design the manipulation of the poison or how I design a poison depend on the omega hat. So now the very interesting question is, what is omega hat? Omega hat is my imitation of the learning algorithm. What would the learning algorithm do, right? If I design my poison, the learning algorithm would use the poison training data to train a neural network. And the omega hat is gonna be my estimation of what the learning algorithm will get after using my poison data. So you can see there is a convolution here, right? This omega hat depends on my DC, but my DC also depends on my omega hat, right? If you can see the inner optimization, it is omega hat that is arg min of a loss function that, the loss function is just the imitation of the learning algorithm, right? So it's essentially the training data. Of course, if you don't know the training data, it's gonna be detraining of the hat, right? Your estimation, your surrogate training data, union of the DC prime, right? So you have the training data, you also have the poison because I'm going to inject your poison. So that's very interesting. You can see this DC prime is also appeared here. Okay, so using this poison training data set, then I'm gonna find omega hat that minimize my loss function. Okay, so that's why it's a bi-level optimization, because this loss function depend on omega hat, and this loss function depend on DC, right? The outer one is optimization over DC, but depends on omega hat, and the inner one is optimization over omega, but depends on DC hat. So that's why when I was, without introducing the notation is a little bit confusing too, or is a little bit not so easy to describe the bi-level optimization problem, but here it becomes more clear. Hopefully I've resolved some of the confusions before. Okay. So you can see, this is some explanation. The surrogate data is divided into two disjoint sets. You have the training and the evaluation. The training surrogate data set will, along with the poison points, are used to learn the surrogate model, right? So that's why, in this inner optimization, you have this omega hat, which is the result of this arg min optimization, right? And the hat of the validation, surrogate validations that is used to evaluate the impact of the poisoning examples on trained data. And the attack objective is the loss function that evaluates the performance of the poison surrogate model on the surrogate validation set. So, one might ask why this is deval of hat, right? Because usually, sometimes people, if you have a, you don't want to evaluate how, so, this is very important to notice that this is deval hat rather than the training hat, because you don't want to simply evaluate how bad you've caused the model for training data performance. More importantly, you wanted to cause the model to misclassify during test. So that's why they kind of divide the D into two disjoint sets, and they want to evaluate the loss on the validation set. So that's very important. And that's the objective of the attacker, right? The attacker does not only want to cause performance degradation in training, it's more important wanted to cause performance degradation in test. So that's why they use validation set here. And it's very important. Any questions? So this is just, the description of the error generic poisoning attack. So it's a bi-level optimization problem. Now, as we talked about before, there was this error specific poisoning attack. Only difference now is that, now the objective function of the attacker is not on the L, but rather on this minus L of D val prime hat. What is that? So this D val prime hat is a set that contains the same data as the validation, the surrogate validation set, though with different labels. So it is a little bit hard to understand. So basically, the attacker can choose, they can choose a different label, basically do a label shift of the surrogate validation set so that they can effectively aim at minimizing the loss on the desired set of labels. Right? So overall, these two frameworks are very similar, and you can think of it as just a uniform framework. But the only difference here is just how you select the attacker's objective function. But nonetheless, the difficulty of solving these bi-level optimization problem is not affected. It is the same. Okay. Any questions? Okay. And this is, very interesting thing, I don't want people to miss here. It seems to be maybe the most important slide in today's lecture. Okay, so as I said before, this paper said that's, this gradient-based poisoning attack basically does not work. I mean, it works for a lot of traditional tasks, SVMs, linear regression, and so on, but it doesn't work for DNN. And this paper will tell you why. Okay, so first of all, it is going to introduce how you can use gradient descent, or actually gradient ascent, to design poisoning attacks. So for simplicity, they assume that there's only one poisoning, you only poison one point at a time. So only one training example is being poisoned at a time. And they're going to denote this with XC. So XC is just one training example. And the label of XC, which is denoted as YC, is initially chosen by the attacker, right? So what this means is that it's gonna be non-adaptive. You can only do this once. You don't want it to, change the label of the attacker during the training process or so. So what is the objective function now? What is the optimization problem now, right? So still you have to design the DC star. So what is DC star is how you manipulate the data, how you design the poison. So it is essentially just an arg max of the attacker. So since I said this is just one poisoning point at a time, so the poisoning only is going to design one poison data point. Okay, so this is a XC prime. And this XC prime will be evaluated, will be used to evaluate the object function of the attacker. Okay. And in this scenario, the object function of the attacker is just the loss function evaluated using the validation set and the W hat, right? Just like what we see before. And W hat, of course, is just the loss function evaluated, the training loss, arg mean of the training loss, and the loss is evaluated based on the surrogate training data set, as well as this poison data, right? This is just one data point. So it is XC prime, YC. This is just one data point. Okay. Of course, this training loss is also evaluated on this omega prime here. Okay, so your omega hat is just arg min of the omega prime. You wanted to solve this problem, right? This is nothing but a rewrite of the bilevel optimization problem we see in the previous slide. The only thing that's different is that we are looking at one poisoning point at a time. So after that, the gradient-based poisoning attack is going to do the following. Okay, so what it's gonna do? The gradient descent. So because if you assume that the loss function is differentiable with respect to XC and omega, then what happens is it's gonna take gradient with respect to XC on the object function A here. Of course, I'm omitting this part here, but you can see this is just the taking gradient of A with respect to XC. A is the object function of the attacker. And based on the chain rule, you will see it's gonna be gradient of L with respect to XC plus the gradient, the partial derivative of omega hat, based on with respect to XC, and then the gradient of L with respect to omega. So this is very important. Based on the nature of the bilevel optimization, based on the convoluted dependence between the outer and the inner optimization problem, if you take the gradient of the objective function of the attacker with respect to XC, you will have this term here, right? This part is to, first part, this is just to take gradient with respect to XC. Of course, this L depends on XC, but this part is also taking into the account that it also depends on omega, right? So that's why, we're first taking the partial derivative with respect to of omega with respect to WC and evaluating on omega hat, but it's also taking derivative with respect to omega on the L. This is nothing but the chain rule here. Any questions here? This is very important. I think if you have a misunderstanding here, then it's probably very hard to understand what we'll talk about later following this. Essentially, the difficulty is really to evaluate this guy here. Right, how do you evaluate the partial derivative of omega with respect to XC? Evaluated at omega hat. Okay, so if there is no question, I assume that it's fine. So let's move on to understand how we can come up with this omega, partial omega divided by partial xc. So using the stationary conditions, the KD conditions, so under some regularity conditions, for example, if you assume that your loss function is just convex, that this is the training loss function, is convex, then you can compute the partial omega hat divided by partial xc by replacing the inner learning problem with its stationary conditions. Okay, so this is, the claim here, and this is how they're doing it. Basically, they're going to replace the inner optimization with the implicit function, just setting this training objective to be 0, the gradient of the training objective with respect to omega to be 0. Of course, this is evaluated on omega hat as well. So this is quite interesting, right? So you are setting this to be 0. Now, what happens is that you can also take gradient with respect to omega as well as gradient with respect to xc, then you're getting this linear system. So I'm gonna pause for a second. Let me understand why we can get this linear system. And if you do have a question, please, ask, and we can have a discussion. Why we can have such a linear system. Yeah, I want to remind everyone of this function here. So taking derivative with respect to xc is just this term here. Notice that there is the vector here. So this vector transpose with the gradient of L. Okay, so once you see that, then you can see why we have this linear system here in the green. Why? Yeah, so from here, what I'm really doing is I'm taking an extra, object, I'm taking an extra gradient with respect to xc, right? It's still gonna be 0. So what I mean is like the left-hand side and the right-hand side is all taking an extra gradient with respect to xc. And this will give you this linear system here. Okay. Okay, so once you see that, then it's obvious to see that, if you replace this, so what I mean is here, right? So if you replace using this linear system, you would solve for what is this partial omega hat divided by partial xc. It is nothing but minus of this term divided by this term, right? So essentially that's what's in my box here. So I'm just replacing this term with that, and this is nothing but the update rule we can use to calculate the gradient of A with respect to xc, which is in the previous slide. Okay. Does this make sense? So, if you assume that this is not singular, then this is going to be an iterative update rule. I'm gonna pause for like 1 minute so people can have the time to ask questions or have a discussion. So the takeaway message here is that you wanted to, to devise the xc, right? To devise the poisoning for that one poison you are allowed to do. So to do that, you wanted to take gradient with respect to that xc. Take gradient with respect, take gradient of the objective function, right? That's how you solve a maximization problem, right? Just take gradient. And then you just, using gradient descent, or, if it's maximization gradient ascent, to find a solution using an update rule. So basically, the most important thing is to figure out how you calculate this gradient. Because of this bi-level optimization, the nature of the convoluted nature of these inner and outer optimization problem is not easy. So this is a way of using stationary conditions, assuming, of course, is assuming that L being convex, then you can just set the gradient to be 0. You get a linear function. Using that linear function, you will be able to calculate how does this partial derivative can be calculated, right? It essentially depends on these two terms. And overall, you would get a update rule for updating the poisoning, how to devise the poisoning. Yeah, so is the Hessian usually non-singular? That's not sure, right? We don't know. But if it's L is convex, then usually, right? So then that's fine. But if L is not, then we have a problem. We might have a problem. Does this answer your question, Chen? Chen, is that fine? Okay. All right. Any other questions? I don't know why people are a little bit like quiet today. Okay, so this is the algorithm. You can see, you have the surrogate training and surrogate validation. You have the objective function during training. You have the objective function of the attacker. You have the initial poisoning point, right? So this is a gradient descent or gradient ascent algorithm. You're going to have an initialization. This is your initialization. And you kind of, you initialize this label to be YC. And you have a learning rate and some small positive constant. Now, what you do is you're repeatedly doing this recursion. What is the recursion? The recursion is first you imitate the learning algorithm, right? So you would imitate, if I have such a poison, how would I learn my neural network? What is the learned neural network? So if I have such a poisoning in my training data, I would learn an omega hat. Okay, so this is just imitation of the training of training the neural network. Now, once I know this is, what the neural network would do, I will just do a projected gradient descent or gradient ascent, right? So how do I do that? This is just a projection, right? We'll talk about it, later, but first let's look at this update. This update is nothing but a gradient ascent, right? So you have the previous point xci at the ith point. Ith time, you would think about a time, then you have a learning rate and you have the gradient. And this gradient, as we said before, can be calculated using, the equation here, right? Now, so once we have this gradient ascent, you have to do a projection. Can someone tell me why I have to do a projection? This is pi of theta, and this theta is something like the data manipulation constraint. So do people see why we have to do a projection? Yes. Okay. Maybe we're just like a little bit reluctant to talk today, but that's fine. So the projection is just like, you have to make sure that the manipulation is not too large. The manipulation is like some L norm bounded, or the deviation from the poisoning to some clean data is not too large, right? Based on your threat model. So let me go back. I'll just take 1 second to go back to the definition of the theta so that people understand it, right? Okay, so here, this is the data manipulation constraint, okay? So it's the space of possible modifications you are allowed as an attacker. Does that make sense? Right. So, people are more familiar with this L norm, LP norm bounded, L infinity norm, L1 norm, L2 norm bounded things. But that's not the only, in order for this to be more general, that's not the only constraint we will consider. You can consider any kind of constraint. Okay, so that's my description of the gradient ascent. I hope this is clear. Right, so once this thing, the update on the once it reaches some convergence region, I mean the convergence is evaluated based on the difference between the attack objective function being, the difference being smaller than this threshold. Then you would output the final poisoning point, XC. Okay, so this is the gradient ascent. And, most interesting thing is that how you evaluate this gradient here. Okay. Let's see. So that's a very good point. And yes, right. So, for notation simplicity, we're just talking about 1 point, but yeah, definitely can do this in a batch. And Christine is asking if a specific example fails to satisfy the constraint, what happens? Fails to satisfy the constraint. Are you referring to this pi theta?
Yeah, to the
right. So it's gonna be a projection, right? So if the constraint is the L2 norm is 1. Then, if you don't have, if the vector has a greater than 1 L2 norm, then you have to project back to this L2 norm being 1. So it's a projection, it won't satisfy, but the projection will make it satisfy the constraint.
Oh, okay, I see. Got it. Thanks.
Yeah, no problem. Okay, great questions. All right, so any other questions? And we're not done yet, right? This is just the review of, what the paper claimed that this is what people would usually do, but this is not the right thing to do. Okay. Right. So again, let's review how we calculate the gradient of the attack with respect to XC. It is this very complicated function, and this involves inverting a matrix. Right. Omega is a vector, L is a scalar objective. Then the Hessian is a matrix. You have to invert the Hessian. Just imagine a neural network. It is almost impossible, right? So that's why they say the drawback is computing and inverting Hessian cost p cubed time and p square memory, where p is the dimension of the W, or of the omega, sorry. Okay.
Did you say that L was the neural network?
Oh, L is the loss function. Did I say that? L is the neural network? I didn't mean to. What's your question?
So this is the derivative with respect to the weights or the input?
Weights. Omega is the weight. L is the loss function, right? The training loss function. Let's go back to this.
And it's the weights for the neural network.
Yeah. So, this, you can see, I'm always using omega to denote the weight of the neural network, right? That's what my training is doing, right? How do you train a neural network?
I was just worried that the gradient doesn't exist if it's not differentiable.
Usually you would assume it's differentiable. Yeah, this is making that assumption.
So is that assuming you're not having any ReLU? Because ReLU is not differentiable, right?
Well, so, people have, for a neural network, you would know how to. Yeah, so at those points, you won't, how to say, it is differentiable with respect to the weight, right? No matter whether you have a ReLU or not.
But the output is the weight times the input in through the ReLU. So you would need to take the derivative of the ReLU.
Yeah, so this is a very good question. I'm gonna ask someone from the audience to answer this. I think a lot of you would know how to do this, or what's the explanation of this. Jiahao?
Hello.
Yeah.
Are you checking whether I'm here?
No, I know you're here. I'm just asking whether you wanted to answer
Yeah. So
Michael's question.
I think the hashes and the
No,
the
he's
gradient.
asking about the ReLU, which is, when you learn, when you learn the backpropagation of a neural network, you would learn that, right? Just
Yeah, so
why
basically
it is
that's only
differentiable with
one
respect
point that the ReLU is not differentiable. And so basically given any input and so I think with probability 1, the neighborhood is actually differentiable. So and a Hessian and gradient is actually a local property. So we can assume actually the whole neural network is differentiable. But I mean, if you really lines at that point, I don't think, I have no idea how to define that. And the possible solution is that you slightly change the ReLU such that, it's actually differentiable around that.
Yeah, so people just don't consider the singular point of the ReLU when think about the derivative of the ReLU. Or sometimes you could think about subgradient rather than gradient. So
But the thing is, if you want to do an optimization, then you need to check the derivative, assuming it's differentiable everywhere. And otherwise, you may not be optimizing.
Okay, so I'm gonna ask people, what are we doing in practice? Right, so if that's the problem, that's indeed a problem, right? But if we don't know how to solve this problem, then we cannot learn any real neural network. Do you agree? So I'm gonna ask everyone, since some of you are working on deep learning, can you tell me how do people deal with this in practice? This is not within the scope of today's lecture, but since someone is interested, maybe we can have a discussion. How do we do that in practice? How do you calculate the ReLU, the derivative of a ReLU? Let's say ReLU of X, what is ReLU? What is the derivative? I mean, we learned this in undergraduate intro to machine learning. Please don't be shy. Please just speak up.
I think the derivative is just 1 when x is positive and 0 when it's negative.
Can you speak up? I cannot hear you very well.
I said I think the derivative is just 1 when x is positive and 0 when it's negative, right?
Yeah, that's usually what people are doing it. And when it is exactly at 0, I think I don't actually know how people deal with when it's exactly at 0. Maybe like PyTorch has its own, either set it to 0 or set it to 1. I don't know.
Okay, yeah, I understand that you can do this in practice. I just think that none of the theory works.
Yeah, I don't know how to interpret your sentence of why none of the theory works, but I think you could also think about subgradient and some approximation and so on. Also, it seems like this is in terms of probability, the probability that you will add the singular point is 0. So since this is already, end of the lecture, so I'll just conclude by saying that, so, I just wanted to conclude saying this slide, solving one linear system per parameter, this is very expensive. And essentially, this is why gradient descent doesn't really work, especially if you're working with a neural network. There are some mitigations using conjugate gradient descent, but still it won't work very well. So next lecture, we'll talk about a possible solution for this. And then hopefully we'll finish covering that pretty soon. And I wanted to talk about the defense of poisoning attack, which is something we are, our ultimate goal of understanding attack, right? Which is for the defense. So that's today's lecture. Thanks, everyone.